noticed that typically in this class I've just left the slides for you for reference. We haven't really looked at them too much, but in this case when we do exploit development there is a little bit of background I need to give you from the slides. There's plenty more slides for this section other than the ones we're going to look at, so by all means do take a look at them for your reference as you work through it. But let's take a look at a few little reference slides before we begin the hands-on portion of exploit development. So here on this first one we do have a somewhat dumbed down version of what a program looks like in memory. If you're familiar with this already, you'll notice some of the sections actually aren't there. Like there's a BSS section for non-initialized data that's not shown here in the picture, so it is not a complete picture. But what we're interested in particularly is the stack. That's where we're going to be doing our exploit development. We're going to stick to stack-based buffer overflows. There are certainly other kinds of memory corruption exploits, but we're just going to look at the basics of stack-based buffer overflows. So we are particularly interested in this section here. The stack, notice that the stack starts at high memory and grows towards lower memory. So you can think of it as kind of upside down. And if you forget that, when we actually look at memory, we'll be reminded of that. But high memory to low memory is the stack. Also, we need to know a little bit about our registers. You can think of registers as just a place to store data in the CPU for us to use it. And the registers are going to depend on your platform. If you're working with mobile phones and you have an ARM chip, your registers will be a bit different than what we see here. These are x86 registers, so EIP, ESP, EBP, so on and so forth. The E is for extended. It basically took the 16-bit registers and put an E on the front of them and made them extended for our 32-bit. And we actually really only have to, for this section, know the first three, EIP, ESP, and EBP. We will see an exercise that uses ESI, and if you continue in exploit development, you'll certainly end up using the others, but our most important ones are EIP, ESP, and EBP. EIP is our sort of holy grail for exploit development. EIP, the extended instruction pointer, it holds the memory address of the next instruction to be executed by the CPU. If our goal is to take control of the CPU and make it execute code on our behalf, having control of EIP seems like exactly what we should be after, and indeed it is. We have ESP and EBP, this extended stack pointer and extended base pointer. Those are the top and the bottom of the stack respectively, ESP pointing to the current stack frame's top or lowest memory address, because remember the stack is basically upside down, and EBP, the base, is the bottom or the highest memory address, so it keeps track of where we are in the stack, or in memory where our stack frame is. And again, there will be an exercise that uses ESI, and we'll see the other ones as we look at memory and look at what's in the registers, but really the only three that are very important to us and we need to know what they do are those top three, EIP, ESP, and EBP. So the stack. Again, this is the one that we are looking at here. We're going to do stack-based buffer overflows. So it is a last in, first out, or I guess if we were going to get technical with computer science jargon, I believe they say first in, last out, or last in, first out. I'm not sure. Whichever. You can think of it both ways. But you can just think of it as a stack of lunch trays. The last one that is put on by a cafeteria worker that's clean is the first one that is picked up by a patron. You have to kind of jumble things around if you want to do it any other way. And same way with the stack. If you want to take something off the stack, you only have one choice, it being the thing that's currently on the top. And likewise, if you want to put something onto the stack, you have to put it on at the top. You can't just insert it wherever you feel like. Certainly there are ways of addressing other parts of memory, but using the push and pop instructions, push pushes something onto the stack, onto the top, and pop pops off the top of the stack. So again, I like the analogy of the lunch trays, but whatever makes you understand it well. Alright, so here is an example of a stack frame in memory. EBP is kind of like ridden up a little bit here. It should be down at the bottom. I'm not really sure how that happened. Then again, high memory at the bottom, low memory at the top, and ESP at the top, EBP at the bottom. But when things really get interesting is when we call another function. Typically, when you work with a program, it is going to have more than one function. If we do proper programming, we should definitely use lots of functions. We shouldn't just open main for a C program and then just write everything we're going to do in there. But even if we do, chances are we're going to call some built-in function of some kind, like to make it print to the screen, for instance. We would call something that's built into C, so we would be calling another function even if we don't make a second function ourselves. It would be fairly difficult to do anything useful without calling some function of some kind. So chances are we're going to have our main function call another function at some point. When that function finishes, it may even call other ones, so you end up with lots of functions called. But when our function finishes, it needs to return back to main. So we need some way of keeping track of where it should return to. It shouldn't just start at the beginning of main again. It needs to pick up where it left off. So we need to store that somewhere, and that is the meat of what we're going to be doing. Is we're going to take that saved return address and we're going to manipulate it. So how this works in x86, again, it varies. Like ARM does it a little bit differently, but ultimately, logically, it comes out about the same. But there's really no like set way you have to do this. But for our x86, how this is done is when another function is called, before the stack frame for the new function is pushed onto the stack, well, is wound onto the stack. It's a little bit different than just push, 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 push. We can actually look at the assembly for that. It's basically it adds, or rather subtracts, because we want to move to lower memory, ESP, to make some new space. We'll see that. Getting a little ahead of myself. But anyways, before we do that, we actually save the return address. So we take the next instruction to be executed in main, or our currently executing function, and push it onto the stack. So we just save it there right on top of main stack frame. And then we create a stack frame for our new function on top of that. And then when the function finishes, its stack frame pops off and or is unwound, because again, it's not just pop, 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 popping off data. It's a little bit more complicated. We'll see that if we look at the assembly. But then we get rid of that stack frame, ESP and EBP. Then we'll need to move back into main stack frame from the function. And we take that saved return address that's right on top of main stack frame and we load it into EIP. So it returns as though we never left main at all. We just pick up right where we left off. So here's another little example here of what it looks like in memory. So we have main stack frame again. We have that return address, so that is the memory address to return to in main. So next instruction we want to execute when our function finishes. In this case, I've called our function function1. And we have ESP. While function1 is executing, ESP will be at the lowest memory address or top of function1 stack frame. EBP again kind of looks like it's gone up a little bit, but it is pointing at the bottom of the current stack frame, and it also has, in this case, the saved EBP from main. So we basically, at the bottom of function1 stack frame, have our saved EBP. So what will happen when it finishes, we'll bring ESP back down to EBP. We'll get the saved EBP from main, move EBP there, and then, so basically we'll pop that off into EBP to restore EBP. So ESP, since we popped this off, will now be pointing here. That'll be our return address. We'll return to it, so we'll load that into EIP. So whatever is here, which should be our saved return address in main, since we're doing exploit development, you can imagine we might want to put something else there to get control of EIP. That is in fact exactly what we're going to do in this section. And then if we pop that off, then ESP will now be pointing back at the top of main. We will have restored ESP and EBP. So again, we can see that with the assembly if we look at our assembly instructions. If you're not familiar with assembly, don't worry, no requirement for that. We're not really going to do too terribly much assembly in this class. Just the little bit we need in order to work through this. But that's just a general idea of how this works. So again, just a little bit of theory here. Just remember our registers EIP, ESP, and EVP, and kind of get an idea of what this looks like. When we actually look at a program, we'll see how this works. We'll see that it actually does follow the theory, which is nice. So with that, let's stop playing with slides and actually go ahead and look at it.